Hey class, to start this next chapter off, I am going to introduce this simple model that has to do with rabbits and foxes. So this is a population model where we assume that the number of rabbits and the number of foxes only depend on each other. So foxes eat rabbits. So the assumption that I made was that for next year's rabbits, there's 2 times the number of rabbits this year. They multiply, right? And minus the number of foxes this year. So foxes need to eat the rabbits. And if you're worried that, hey, that's not enough for foxes to live on for a year, we're going to change the scale, and this is going to be thousands of foxes and just hundreds of rabbits. So it takes about 10 families of rabbits to feed one family of foxes. And the number of foxes next year only depends on the number of foxes this year, 1.1. So they don't grow as fast. So if we have 100, then next year we'll have 110 foxes. So you might notice that this is actually a linear system. So for rabbits next year, I'm just going to call it R. We'll just call it Rn, little n though, for year. Here we'll use Rk. And that means it's 2 times Rk minus 1 minus foxes in the previous year. And the foxes in the kth year will be 1.1 times the foxes this year. Okay, so simple system. We can write this as a matrix, and we end up with the rabbits this year and foxes this year. Think about that as a population vector that is 0, a minus 1, 1.1 times last year's population, R k minus 1, foxes k minus 1. So here we have a system. And what I did was I set up a GeoGebra sketch that helps us see what happens over time. So I can start with an initial population, multiply it by this matrix to figure out the next year's, but then I can multiply next year's by this same matrix to figure out what the next year's would be, and the year after that, and the year after that. So let's go to the GeoGebra one. So here's the GeoGebra setup. Now, this red one is the population in year 1, and then it moves to this one that's population year 2, population year 3, and moves over to the right. And as I move this dot, it changes what happens. I can move it way up here, oops, and it looks like we might be in trouble because the dots go over there. What's happening? Well, let's start down here. Okay, this means that there are actually there's a lot of rabbits, almost 1,000 rabbits here, and there's only 10 foxes. So there's not very many foxes compared to the number of rabbits. So the rabbits are going to easily multiply, and the foxes already don't grow very fast. So they're going to go, the rabbits are just going to keep almost doubling. There's very few foxes to impact the growth. Okay, as we go up here, you'll notice we're still keeping about the same number of rabbits, but the number of foxes is growing, and notice it's impacting the growth of the rabbits. We can't get quite as many every year. They're getting pulled back towards this population of year 1. Okay, what happens if there's a lot of rabbits, a lot of foxes and not very many rabbits? So then there's 2, let's see, yeah, so there's so many foxes here compared to the rabbits that the population of the rabbits actually goes down, and then they go down again, and then the foxes eat them all. Like, you can't have negative rabbits over there, but the rabbits die out. So, so I'm going to move this around a little bit. Oh, what happened right there? Look at that. Let's go back. Oh, there is something happening right around there. If we go over this way, then the rabbits are happy. They might not grow very fast at the beginning, but they're still really happy. Foxes are still growing. If we move over here a little bit, then the rabbits are not happy. The foxes won't be happy because their food's all going to be gone. But man, there's some place in the middle there that something's happening. Here, I'm going to get this to a couple values that I know will work well. I hope I can get this to work again. Oops. Can't see that. There. No, that's not what I'm trying to do. Get to 0.72 here. Okay, there's 0.72. Now, keep inching over until something happens. Oh, look at that. Look at that. What is happening here? The population just stays on the line year after on one line year after year after year. It's pretty amazing. So there's no craziness going on. This is the same. We don't need a fancy matrix to figure the population out year after year with this. If it lies on the same line, that's just a scalar multiple. So we don't need a 2x2 matrix. We could just use a scalar. There's something like magic about this line right there, this spot, or dots on that spot. If I move this up and down a little bit, oops. It's a little bit too sensitive to try to do this, but any point on that line, if I could keep that spot on that point on that line, it would still produce that same effect. There's actually one more line that has that property in this. We could start with 0 foxes. And if we start with 0 foxes, then the rabbits, according to our model, the rabbits are going to double every year, right? Because there's no foxes to eat them up. So, so if we start with 1,000, then we end up with 2,000 the next year, and then 4,000 the next year. We just keep on going. All of these actually all lie in the same line. And here we just start with the population of, if we have 1,000 rabbits and 0 foxes, then we can multiply by 2 and we'll get the next year's and multiply that by 2, and we'll get the next year's, multiply that by 2, and we'll just keep on going. So there's something magic happening along these two lines, okay? That magic that we're trying to figure out, they have everything to do with eigenvectors and eigenvalues, okay? And that's going to be the main study of chapter 4. Eigenvectors and eigenvalues are arguably the most important thing to understand about matrices, because they tell you so much about the transformation that's happening and about the system that they describe. So in this case, if I can get this back up to about where we were. Okay, I had to stop recording for just a moment. My son stopped by, and he took linear algebra about a year ago, and I told him what I was doing, and he told me to tell everyone that to make sure you understand that eigenvectors and eigenvalues are very, very important, and that they're going to come up for the rest of the semester, because he didn't learn them really well when they first came up, and he didn't think they were that important, and thought, oh, this is a one-section sort of thing. And so he ended up not doing so well the whole rest of this section, the whole rest of the semester, because a lot of what we do for the rest of the semester depends on eigenvalues and eigenvectors. So they're not just a one-section thing. We're going to use this to build up lots of other mathematics and understand linear transformations and matrices and matrix operations. So take this seriously, learn this well. So where were we at? This line down here, we talked about this. Any vector or point on here, if we represent a vector from the origin out, it's an eigenvector of the matrix that we started with. I have the matrix somewhere over here. Yeah, M here, 2, -1, 0, 1.1. And that other thing up here, that other magic spot up here, anything on that line, on that magic spot, it is also anything on that line is also an eigenvector. And those tell us lots of things about the system. So I put an equation to that line, any vector on this line, if you multiply it by the vector m, it's the same as just multiplying it by a scalar. That particular scalar is called an eigenvalue, and the vector is called an eigenvector. So each matrix has eigenvectors and eigenvalues associated with it. And we'll talk about how to find them in just a moment. But just to show the importance of it in this situation, this line, this eigenvector that we're on, that line, it separates this system into two areas. If I'm over to the right of this line, then the rabbits will live, their population will be healthy and successful. But as soon as I cross that line, even on that line I'm okay, but as soon as I cross that line, boom, the foxes eventually are going to eat up all the rabbits. So, which isn't good for the rabbits or the foxes. So, okay, let's jump to my notes. All right, so if we call this our matrix M, okay, then the eigenvalue, if we have a vector V, well, let's call it X. The book calls it X. If there's a vector X that's the same as just multiplying it by a scalar, see, then if this is the case, then X is an eigenvector, and C is an eigenvalue. So these match up. So the eigenvector is associated with a particular eigenvalue, and eigenvalues are associated with a particular eigenvector, sometimes a set of eigenvectors. So how do we go about finding these? Well, we actually use this equation. So, but first, before we find them, I should say that the book, and it's pretty standard to use the Greek letter lambda. You may not have seen this before. So this is L-A-M-B-D-A, lambda, okay, to represent the eigenvalues of a matrix. So I'm going to go ahead and change that now so you can start getting used to it. So lambda. So if this is the case, then we can say, well, mx bar minus, we're going to pull the right side over to the left side, lambda x equals 0, and we can factor out the x. So m minus lambda, we'd have to be, so this is a scalar, but if I think about lambda times, I have to do one tricky thing here. Okay, just to illustrate the problem we're having, if this is my matrix and I'm subtracting times x minus a number, I'm just going to pick 2 times x. It doesn't make sense for me to factor out the x right there, because then I'd have a matrix minus a number times the x vector. This is undefined, like this doesn't mean anything, but we can rewrite this as 2 times the identity matrix times x. These are the same things right here. You still just get double the x vector, and so that's what we do over here to factor it out. We have lambda times the identity matrix times x equals 0. So that means we can find our lambdas and our x's if we write down this system and look for the null space. Look for all the vectors that we could multiply by this system, by this matrix, and get 0. So in practice it looks like this. I'm going to take, I'm going to actually write down m minus lambda I 1 0 0 1. Okay, and we want to know when does that x equals 0. This is the 0 vector. So I can multiply in by lambda, so minus lambda 0 0 lambda, and here 2 minus 1 0 1.1, and now I can do the subtraction. And so I get 2 minus lambda minus 1, 0, and 1.1 minus lambda. That times x bar equals 0, 0. And there's a couple different ways we can do this. We have two options. One, I can augment and solve, and augment and row reduce. I can also use the determinant. So if the determinant is not 0, then the null space of this matrix will just be the trivial solution. So if we want to have something besides x just equaling 0, 0, then we need to have a determinant that equals 0. So with the 2 by 2, the determinant's pretty easy. I'm going to take these terms and multiply them. 2 minus lambda times 1.1 minus lambda minus, and then I get 0 times a minus 1. So subtracting that, the multiples along those diagonals, that has to equal 0. Well, we're lucky here because this is 0, and so we just end up with 2 minus lambda times 1.1 minus lambda equals 0. And it's already factored down for us. That means lambda equals 2 and lambda equals 1.1. Those are the two values that we could use. These are our two eigenvalues. And these are, if we go back to the system, one of our eigenvectors, when we were on the x-axis, our rabbits were doubling. That's the significance of that too. Anywhere when we were on that x-axis, it doubled from year to year. When we were on that other line, that other magic line, is both populations grew 1.1, or by a factor of 1.1. 1.1 every year. Okay. So now let's try to find the vectors that are associated with both of these, the eigenvectors. So if we, I'm going to take lambda, let's start with lambda equals, well, let's start with lambda equals 1.1. So I'm going to go back up to this equation, this matrix here, and I'm going to plug in 1.1, and then I am going to, we're going to find the null space of that. We're going to find all the vectors that we can multiply by this matrix. And get 0, 0. So, so if I do the, let's do the subtraction. Here I get 0.9, here I get -1, here I get 0, and here I get 0, 0, 0. I want to have this to be 1, that entry to be 1, so I'm going to multiply everything by 10/9. So I'm going to get 1, a minus 10/9, 0, 0, 0, 0. And now I can figure out what the solution to the system is. So here I have x minus 10/9 y equals 0, and I also have y equals y. I have one free variable here, right? So you better have a free variable when you do this, otherwise you don't have the right eigenvalue. So that means I could write this system as xy equals, well, let me do it down here first. So x equals 10/9 y, y equals y. So I could write that right side as y times 10/9 1. So x, so I'm going to replace this with a parameter t. So t is 10/9 1. So I just did the procedure that we do to describe infinite solutions. There are infinite solutions here. Any multiple of this vector will be any multiple of this vector. It'll be in the null space of this system, but it also means that any multiple of this vector, if I multiply it by our original matrix M, where's my original matrix? So if I multiply it by this matrix, then it should just multiply that vector by 1.1, because this is associated with the lambda equaling 1.1. So this is our eigenvalue. Just do eval, and this is the associated eigenvector. Okay, let's test that. So if they give you a vector like 10, 9, and 1, and they say show that this is an eigenvector, show that this is an eigenvector of, and they give you a matrix, here's this, and 2, minus 1, 0, 1.1 of that, then what are you going to do? Well, let's multiply them, because if it's an eigenvector, then multiplication of this should be the same as just multiplying by a scalar. So let's check. So 2 minus 1, 0, 1.1. 10.9, oops, I'm sorry, 10 ninths. 1. So 2 times 10 ninths is going to be 20 ninths. 20 ninths minus 1. And then 0 times 10 ninths, and then we get 1.1. So that's, let's simplify that. So 20 ninths minus 1, we should do 20 ninths minus 9 ninths, and that gives us 11 ninths and 1.1. Oops, don't want to have my fraction line there. Well, is this vector the same as multiplying this vector by a constant? If so, what constant? Well, if it is, it has to be 1.1, because 1 has to go to 1.1. Is 10.9 times 1.1 1.1 ninths? And it is. So this is the same as just taking 1.1 times 10 ninths times 1. So you get 1.1 ninths. 1 there. So if you multiply that vector times 1.1, that's the same thing as multiplying by the matrix. Multiply the matrix by that vector. And it actually doesn't have to be that vector. It could be any scalar multiple of that vector. So an easy scalar multiple of this vector is let's multiply it by 9. Let's get rid of that fraction. So we have 10, 9. Okay? So 2 minus 1, 0, 1.1. That should be the same as, so I'm going to put question mark, is that the same as 1.1 times 10 ninths, which is 11. 11 and 9.9. Is that the same? Well, let's go down here and figure it out. I get 2 minus 1, 0, 1, 1, 10, 9. 2 times 10 is 20. Minus 1 times 9 is 9. 0 times 10 is 0. Plus 9 times 1.1 is 9.9. Sure enough, we get 11, 9.9. Okay. So we found both eigenvalues. So 1.1 and 2. So those are our two eigenvalues. The eigenvector associated with 1.1 is this. Sometimes they'll write it as like the basis. They'll write it as a basis and say it's 10, 9 or 10 ninths over 1. 10 ninths 1 is the basis for the null space associated with lambda equals 1.1. And I think it's, we're not going to find the vector for 2. We won't go through and do the work. It ends up being, since we already know it lies on the x-axis, remember, because it just kept multiplying and doubling the rabbit population this way, it ends up being 1, 0 is the eigenvector. So we won't go through and do the work. You're welcome to do that. So for lambda equals 2, 1, 0 is the E vector, the eigenvector, not E veggie. Okay. This goes through a lot. What I did goes through a lot of what the slides did. It just uses that one real life example. But I'll just hit a few high points. Here's, if they have a, on the previous page, they have a vector, a matrix and a couple vectors, and they do the matrix multiplication. One of them ends up just stretching it, and the other one ends up doing something weird. It does stretch it, but it also rotates it around. So this V is an eigenvector for A, because when you multiplied A times V, it was the same thing as just stretching that out. So we've already talked about that. No, only n by n matrices can have eigenvectors and eigenvalues. So we're only dealing with square matrices. They don't have to be invertible. But eigenvectors and eigenvalues are only associated with square matrices. Which of the following vectors are eigenvectors, and what are their associated values? Well, you just have to multiply A times each of these and see if it's the same as multiplying by a constant, and whatever that constant is. Like in terms of U, it ends up being just 5 times that vector, the same as 5 times that vector, so 5 is an eigenvalue of the vector 398. Eigenvector of A with, so U is an eigenvector of A with the eigenvalue lambda equals 5. So find the eigenvector. So here, this is an example. We've already done an example like this now. They give you a matrix. They say here are the eigenvalues. Find the eigenvectors associated with these eigenvalues. You set up the matrix like we did, where you take the matrix minus the lambda, or whatever it is, minus the identity, and you end up with a new matrix. And then you row reduce, or you can think about it as augmenting with the 0, 0, and finding out what solutions there are there. And it turns out that this is the basis, so you have anything times this value, any y or t times that is an eigenvector. So any multiple of this 1, 1 is an eigenvector. And then you do it with the other one. So they said 3 was one option. They said a -1 was another eigenvector. So you just set up the same way, then you row reduce, and you end up with this as your eigenvector associated with a -1. I think we'll finish the rest of this in class, but that should give you enough to do your homework. You're certainly welcome to go through and look at these examples that they've gone through. Okay, thanks.